Based on the audio features we have mentioned before, we not only can do audio signal analysis and also do the music genre classification. Now we can also apply the similar audio features and some probabilistic model or machine learning method to do audio effect detection. In the following material, we will describe an example about audio effect detection. And this paper was published in year 2003 in IEEE International Conference on Multimedia and Exploitation. And again, you can see a very familiar name, Professor Dr. Hongjiang Zhang. The paper title is Highlight Sound Effect Detection in Audio Stream. They try to model and detect 3 sound effects, including laugh, applause, and cheer. And they think the sound effect detection is a doable research because they can handle the following cases. They first have to model more particular sound classics, and they try to record the expected sound effects only and ignore others. And the proposed method, the characteristic of the proposed method is they try to achieve high recall and the precision rate, okay, especially the recall rate. And the extensibility. The proposed method should be easy to add or remove sound effect model for new requirements. Therefore, the proposed method should be generic. That is not specific to only laugh, applause, and cheer. That should be a generic model that can be used to describe various audio effects. The first step is still the audio feature extraction. We just briefly described the audio features here because we have already many experience about the audio feature extraction. In this paper, all audio streams are 16 bits, mono channel, and downsample to 8 kHz. That means the sampling frequency is 8 kHz. And each sample point is described by 16 bits, and it's mono channel. Each audio frame consists of 200 samples, that corresponding to 25 milliseconds with 50% overlap. Then they extract features in the following: showtime energy, average zero crossing rate, subband energy, brightness and bandwidth, and the 8-order MFCC. These features are all introduced before. And these features form a 16-dimensional feature vector for an audio frame. And to describe the variation between frames, the gradient features of adjacent frames is also described and is concatenated to the original vector. You can expect the so-called gradient features is the difference between two feature vector. For example, at the time instance t, the features may be x1 to x16, and then at time instant t plus 1, another feature may be x1 to x16 hat. And now the gradient feature is actually the gradient features may be the x1 minus s1 hat, x2 minus s2 hat, and so on. So again, we get another 16-dimensional feature vector, difference feature vector, and then concatenate this 16-dimensional to the original 16-dimensional to form a 32-dimensional feature vector for each audio frame. They utilize hidden Markov model to describe sound effect. Hidden Markov model can describe the time evolution between states using the transition probability matrix. And they use a complete kinetic hidden markup model to model each sound effect with 4 continuous Gaussian mixture modeling each state. For the training data, they collect 100 pieces of samples segmented from audio track, and each piece is about 3 seconds to 10 seconds, and totally about 10 minutes containing data for each class. So they have 100 pieces of laugh, 100 pieces of applause, and 100 pieces of cheer. And how do they determine the numbers of states? Because we still remember, for a hidden markup model, we have lambda is equal to A, B, pi, where A is the transition probability, B is the observation probability, and pi is the initial probability. And now we have already determined for each state, the observation probability is described by 4 mixture, for a Gaussian mixture model with 4 mixtures. And how many states do we have? In this paper, they use a clustering algorithm to determine the state numbers of hidden markup model. So they collect a lot of audio features from the left audio sound, a lot of audio features from the applause with audio sound, and then they do clustering. They finally found that for applause audio features, they can roughly categorize into 2 groups, and for cheer and laughter, they can roughly categorize audio features into 4 groups. Therefore, they finally set the numbers of states for the applause hidden markup model as 2, for the cheer and the laughter hidden markup model as 4. So this is one way we can use to determine the numbers of states when we apply hidden markup model. And then how do we train the hidden markup model and test the hidden markup model? Okay, basically a given audio sound is divided into 1 second moving window. Okay, so this is an audio clip. Okay, and again we need to extract clip level audio features and the frame level audio feature. And right here, a clip consists of 1 second audio signal. So 1 second moving window with 50% overlapping, and each data window is further divided into 25 millisecond frames with 50% overlap. And from each audio frame, we extract audio features. We first determine the silence window. Okay, silence window will be skipped for the following process. And how do we determine the silence window? That is, we check the average short time energy. Okay, because right now we have 1 second. For example, this is 1 second clip, and then we have many audio frames. Okay, and we check the average short time energy. If the average short time energy is less than a threshold, and the average zero crossing rate is less than another threshold, then we will say that this 1 second moving window is a silence window. And for the non-silence window, we will compare against each sound effect model and to get the likelihood score. That is, we will calculate probability O given lambda or log probability O given lambda. So remember that if this moving window is not silenced, then we will get audio feature vector from the first audio frame O1, and then from the second audio frame O2, and so on. Therefore, for each 1 second moving window, we will get the observation O1, O2, and so on to OT. And for O1 and O2 and to OT, each audio feature vector is 32 dimensional. And we are given this sequence of audio features, and then we can apply this. We can input this to the hidden macro model. Okay, and here is the flowchart. So given the audio string, we will extract. We will check the moving window, and then extract features. And then we will input for non-silence window. We will input the extract features to the constructed hidden macro model, and then each hidden macro model corresponds to one sound effect. For example, the hidden macro model 1 corresponding to the laugh sound effect. The model number 2 corresponds to the cheer sound effect, and so on. And we will calculate the log likelihood score, and finally determine which sound effect the input audio string belongs to. There is one thing unique in sound effect detection that is different from audio classification. Unlike audio classification, we can simply classify the sliding window into the class which has the maximum log likelihood score. In audio classification, given an audio sound, or maybe one data window, we just extract features and put it into a hidden macro model, into several hidden macro models like M1, M2, and M3, and then we calculate the log likelihood value like the O given lambda 1, O given lambda 2, probability O given lambda 3. And then we just take the maxima of these values. And finally, if, for example, if this is the largest value, and then we will say that the given audio sound belongs to this class. However, in audio sound effect detection, we cannot do this because for a data window, it may not belong to any of the sound effect. It may just environmental sound. It may just present nothing. Okay, so it doesn't belong to laughter, one of the laughter, cheer, or applause. It may belong to nothing. So we cannot simply classify a given audio sound into one of these class. Okay. Therefore, they design a process in the following. Each log likelihood score is examined to see if the window data is accepted by a corresponding sound effect. Okay, we will check whether the log likelihood score is larger than a threshold. Okay, and the likelihood score may be larger than two predefined score. That means for the same data window, it may belongs to cheer as well as laughter. Okay, because at the same time, people may cheer and laugh, or they may laugh and as well as applause, like ha ha ha. Okay, so we have a laughter and we also have applause. Okay, therefore we cannot just calculate the given data window into one of the audio class. It may belongs to multiple class, or it may belongs to no class. Okay, and how can we make the decision? Okay, in the following, they make the optimal decision based on the Bayesian decision theory. So this flowchart shows that after we get the log likelihood score, we will check whether it's accepted by the corresponding class or not. Okay, and the given data window may be accepted by multiple sound model. And then we will make a decision about whether the candidate it really belongs to some sound effect. And before that, we define a cost function. Okay, this is a total cost. Okay, When will we give a cost? That is when the given sound, the given audio signal belongs to CJ, but we misclassify it into CJ bar. Okay, so or this given sound effect belongs to CJ bar, but we misclassify it as CJ. In these two cases, we have to issue the cost. Okay, so this belongs to two different parts. The first part is it belongs to CJ, but we falsely reject it as CJ bar. Okay, so this is the prior probability of CJ sound effect, and this is the probability that given the CJ, we misclassify it as CJ bar. Okay, and in this case, we will multiply this cost. For the second case, that is the prior probability of CJ bar, and in the case that the given audio sound is really CJ bar, but we falsely think it is CJ. So this is another. This is false alarm. Okay, false positive. Okay, and this is okay. Yeah, this is false positive, and this is false rejection. Okay, false rejection and the false acceptance. And in false acceptance case, we have to multiply this cost. Okay, and we sum them together to get the total cost. To minimize the total cost, we will use the Bayesian decision rule. Okay, and based on Bayesian decision rule, we have to define, we have to calculate, we have to make the probability of Sj given Cj divided by probability Sj given Cj bar should be larger than a threshold. And actually, this value is called the likelihood ratio, because right here, the Sj is the log likelihood score under hidden Markov model of the sound effect Cj. So this value and this value are the probability distribution of log likelihood score of the sample within and outside Cj respectively. And this is called the likelihood function. Likelihood function. Okay, and we want this likelihood function should be the likelihood ratio should be as larger as possible. It should be larger than a predefined threshold Rj. And how can we calculate the threshold Rj? Okay, the Rj is defined as the false acceptance cost divided by the false rejection cost multiplied by the prior probability ratio. Okay, and here the prior probability can be estimated based on the database. Okay, so this term can be determined based on the database, and this term, the cost of false rejection is set larger than that of false acceptance. That means the cost in the denominator is false rejection because it's really Cj, but we think it's Cj bar, so this is false rejection. The cost of false rejection is set larger than the false acceptance because we need high recall ratio. Okay, high recall ratio is more important for summarizing and highlight extraction. Because why do we do sound effect detection? Because we try to as far as possible to detect important sound effect. So we want to miss any important sound effect. Okay, we would rather tolerate some false alarm, false acceptance. That would be okay, but we don't want to miss any important sound effect. Okay, so prior probability can be estimated from the database And in this paper, they don't just calculate these probabilities based on frequency counting. They also try to model these two probability distribution. And they approximate this distribution by a negative gamma distribution. Okay, this is the real data distribution. Okay, the within each class and the outside each class. Okay, and they use the negative gamma distribution to describe these two. So we can model the within class by this distribution, and the outside class by this distribution. And then these two data distribution can be described by this formulation. Okay, so here the probability Sj given Cj, the physical meaning is given the Cj sound effect, the probability of log likelihood score is this distribution, and given not belonging to Cj sound effect, the probability distribution of the log likelihood score Sj is this formulation. And we formulate this by the negative gamma distribution. And this distribution has been introduced to you in the probability course. And then how can we make the decision? Okay, the first abnormal score are prone first. The score whose distance to mu larger than 2 times of the standard deviation are abnormal. So we eliminate them first. And then the window that conforms to this criteria are considered to be accepted by a sound effect. And if it is accepted by a sound effect, the corresponding log likelihood is considered as the confidence. Okay, so it is classified into the I's sound effect if this confidence value, it achieves the highest confidence value. Okay. Here we use an illustration to show the overall idea of this paper. Assume that we have already collect a lot of laughter, applause, and cheer data, and we extract audio features, and then we have already construct the hidden markov model, and then the decision process is like this. Now each oval is a hidden markov model, and we first have to construct the likelihood function for each model. So given given the audio waveform and input this audio we input the audio features from approach to the approach hidden markov model, and then we can get a lot of log likelihood ratio, and then we can form a distribution like this. And this distribution is the so-called within class likelihood distribution. And then we intentionally input the audio feature extract from laughter and cheer to the approach model, and then we can also get the many log likelihood score, and then we form the log likelihood distribution like this. And this is the outside distribution, okay, or the log likelihood distribution outside the approach model. Okay, and in many speech recognition or many audio signal processing, it's also called the world distribution. Okay, so here we have formed these two log likelihood distribution, and then given a test audio sound, we will input this sound to the model, and then we will get a log likelihood score Sj, and then we input this Sj, we consult this J to this distribution as well as this distribution to get the corresponding, for example, if the Sj is here, and then the corresponding probability will be here. So this value will be the denominator. And the Xj in the world distribution is here, and the corresponding probability is this value that will be put in the denominator. Okay, if this given if the test sound is very similar to the approach, okay, it's really an approach sound effect, then the corresponding probability here would be large, and the corresponding probability here would be small. And if the denominator is large, and if the numerator is large and the denominator is small, this value, this likelihood ratio will be large, and it's easy to be larger than the threshold. So this is the idea of how they decide whether a given audio sound is really a sound effect. Okay, they don't directly use the output of different hidden markov model. Okay, they also consult how likely this log likelihood value belong to some sound effect in comparison to other sound effect. Okay, so this is quite important. The most important idea of this paper is this: they use likelihood ratio rather than the likelihood score output by each hidden markov model. And finally, they also utilize the attention idea. The audio attention model is constructed to describe the saliency of each sound effect. And based on the energy and the confidence in sound effect, they calculate the so-called audio attention. And here, the EAVR is the average energy. The average energy divided by the maximum energy is inferred to this value. And Xj is the log likelihood score. Max Xj is the maximum log likelihood score, and then we take the difference and take exponential to be this Pj bar. Okay, and the attention for the class J is defined by the average, the normalized average energy multiplied by the this value P, and then equals the value Mj. And this value means the attention value of the given sound effect. So in previous slides, we have already determined whether a given 1 second moving window belong to a sound effect. Okay, belong to which sound effect? And then this value measure how likely, how strong, or the strength of the data model of the data window belong to some sound effect. Okay, and how can we calculate this value? Okay, we just calculate the normalized average energy of this data window multiplied by how likely the strength, how likely of this data model belong to some sound effect, and then we can get the attention value of this data window belonging to some sound effect. And this is an example showing a given audio string, how the given audio string belong to different sound effect at different time instance. For example, at the for the 20 second, from the 20 second to around 30 second, there is a laughter sound effect, and the curve here shows the attention value. Okay, around 60 second. Okay, we have laughter sound effect as well as the cheer sound effect. Okay, and so on. In the evaluation, they construct a database. Okay, the testing database is about 2-hour video, including a TV show, 30-minute TV show, 30 NBC TV show, and the 60-minute CCTV TV show, and the 30-minute table tennis. And the two kinds of distribution curve, Gaussian and Gamma, are compared. Okay, and this table shows the experimental result. If we model the prior probability by Gaussian, then the precision recall is statistics. If we model by Gamma, then the precision recall is statistics. And we see that the Gamma distribution increased the precision by 9.3%, while just affect the recall ratio by 1.8%. Therefore, by using Gamma distribution, we can largely increase the precision rate, okay, but slightly decrease the recall rate. And averagely, they can achieve a recall rate 92%, almost 93%, and the average precision 86%. Okay, and this value is just for your reference because, of course, the experimental result is totally content dependent, and they may just use simple data to achieve a very accurate result. And the higher recall in this result, we can see that they achieve higher recall, and actually higher recall can meet the requirement of highlight extraction and summarization. So this is what they want to do. What they want to achieve. And in table tennis, reporters' exciting voice would be detected as laughter, and the sound effects are often mixed with music, speech, and other environmental sound. So this is why they achieve worse precision in the table tennis sequence. And finally, these are important reference about audio content analysis. The first one is the canonical music general classification, and the second one is for audio sound effect detection. And if you are interested in more advanced or more detail about audio analysis, or you can refer to these two papers. Okay, and you can also see very familiar name like Alan Hendrick. You also see this name in video change detection. And this is another paper mentioning more advanced audio features for music.